Okay, so there are several different forms of Kepler's laws that one might encounter. And we'll generally be using one of them, but you'll see the other forms coming around. The only difference between the different forms, although they may look pretty different, simply are the units. So we introduced last time the form of Kepler's law that has um, p squared equals a cubed. All right? And in this case, we're imagining a situation, and just to make it a little bit simpler, I'm going to imagine it almost in a circle. So we have an object orbiting about, going around another planet, okay, and going around the sun, and the time it takes for it to go all the way around is the period p, and the distance of the orbit is what I'm calling a. And when Newton came around and looked at Kepler's laws, he derived Kepler's laws from his law of gravity, in that he actually made this relationship more explicit because it depended on the masses of the two objects that are in question, and which I'm going to call the total mass. Sometimes I'll just simply write it as m. So he found out that this was the relationship where m total is the total mass of the two objects. Now, usually the center object is the one that's much more massive. So we'll take it as a given, for the most part, that the total mass will be essentially the center object. This is pretty much true if we have a moon orbiting about a planet, or a planet orbiting about a star. It gets a little funny if we have something like Pluto or a binary star system where the two masses are possibly comparable, but so we can still think of it as the total mass. Now, this relationship, the way that's written here, depends on the units that you measure it in. So the p has to be measured in years. Okay? The A, the semi-major axis, has to be measured in AU, astronomical units, of which one would be that for the Earth-Sun distance. And M total, in this way, has to be written in has to be a number converted to solar units. Now, if you're talking only about stars, then that may not be that big of a deal. Solar units would be 1 would be our sun, 2 would be a star twice as massive as our sun, a half would be something that's half as massive, and so on. I find practically most of the calculations you end up doing are not with stars, but they're with planets or moons, and they end up with and you end up with solar units as a really odd unit, because everything is going to be very tiny. The same thing is true for the AU. Now, if we really write it as Newton wrote it, what we would have is the following. And again, I'm just doing this for completeness. We generally won't be writing it this way. He had essentially that the p squared was equal to a cubed over m total but times funny constant. So there's actually a 4 pi squared, and then divided by g, which is a gravitational constant, and so on. So it's kind of an ugly form. And depending on what units you use for g, you basically would get, p usually would be measured in seconds, a would be measured in meters, m would be measured in kilograms. And again, I find, practically speaking, those units aren't always the easiest for students to use. So what I prefer to use is a form that's pretty much the same as the Newton's form, and I'm just going to specify the units here. So we have p squared, and I prefer to measure them in days. The A prefer to be measured in kilometers, and the M preferably measured in kilograms. because of that, we have an extra little ugly constant that appears everywhere, and that constant is 7.9 times 10 to the 10. And the units of this would be kilograms day squared per kilometer cubed. And although this constant is a little ugly, it's still not. It's certainly it's more convenient than using the Newton's form. It's slightly less convenient than using this form, except for all you're doing when you're using the most simple form of the equation is you're passing the buck. What will happen is you'll be able to solve Kepler's equations very easily, and then you'll have a whole bunch of challenging type conversions. And I find that amount is reduced when you use this particular form.